Hello, good morning, and welcome back to Refactoring Bitcoin. Very often I hear people say things like, this function returns a lambda, or this function takes a lambda as an argument. Well, here's the thing. A lambda is not something that can be passed around. It cannot be passed as an argument. You cannot return it from a function. You cannot even store it in a variable. And you might think, hey, just look at this example code here, right? Here, I'm returning a lambda right here. What is this code doing? No, it's not returning a lambda. And the reason why it's not returning a lambda is that is the following. Lambda is short for lambda expression. And expressions are not returned as such. They are evaluated, and then you are returning whatever the expression evaluates to. Like this expression down here, this a plus b, is also not returning an addition, right? The return type is not changed from addition to multiplication if I replace this plus operator with a multiplies. So, and likewise, this here does not return the lambda, but whatever the lambda expression evaluates to. But what are the expressions evaluated to? Like this a plus b, what is it evaluated to? This a plus b, we say, is evaluated to a r value of type int, or more specifically, a pr value of type int. And an r value is something that can only be on the right-hand side of an assignment. So imagine the following. If I introduce another variable int c, just initialize it with the value. This c here is an L value. That means I can write c and I assign the expression a plus b. Okay, this works. This is compiling. But I cannot do the following. I cannot write a plus b and then assign the value c to it. I get a compiler error. Compiler tells me that an L value is required on the left-hand side, and a plus b is an R value, not an L value. Another difference of L values and R values is that I can take the address of an L value. This is working, right? But I cannot do the following. I cannot take the R value, I cannot take the address of the expression a plus b, because a plus b evaluates to an R value, and the compiler tells me that an L value is required. So let's get rid of that here. So now we go back to the lambda expression. What does the lambda expression evaluate to? It's also evaluated to a PR value of type closure. The lambda expression evaluates to a closure object. And the closure object is an instance of a class with an unique type. So I can show here, if I try to take the address of the lambda, it doesn't work. I get the same error message that I'm trying to take the address of an R value, and an L value is required here. I can also show that the types are unique. If I create 2 times the same lambda expression, and let me assign that to a variable, let's say C1 for closure 1 and C2 for closure 2. You see, those two lambdas are those two closures are initialized with the same lambda expression. But if I now do assert, and I want to make sure that the types are equal, I do type ID of C1 and compare that with type ID of C2. Then, okay, I just need to return here because otherwise it deduces the wrong type. I just return C1. And I see, if I run the program, that the assertion fails. So it shows that those two closures have different types. If I change C2 to C1 here, if I compare this with itself, then obviously it's working. So this was to show that the lambda expression produce instances of unique types. So now let's go back to the original code that we had here. Okay, so far for terminology, right? We are not returning a lambda, we are returning a closure object, which is a instance of a unique type. And it's callable. And here, because we are returning it from the function and we use automatic type deduction, we also return the closure object from this function call add5 here. And then we are invoking the closure in line 14. And this, you see here, we create the closure with the value 5, and then we invoke it with the value 3, and internally we add them, and we see here the program returns 8. So that's working. But what if I want separate compilation? I want to move this add function to a separate compilation unit, even make it part of a separate library. I can mimic that here. So I just move the code down below the main function. And now I need a forward declaration here. And you see in the error message that type deduction does not work, because so the function is used before the return type can be deduced. So type deduction does not work here. We have to specify the return type. But how can we give it a return type if the type is unique, if it's uniquely produced at the place where the lambda expression is evaluated? Obviously, we need some form of abstraction. The classical object-oriented approach for abstraction is to create a common base class for the things that we want to handle. And we know, and then make the function virtual that we want to give polymorphic behavior. In this case here, this function is the function call operator. So if we just start like this, so we create a class, and I call it function. And since it's taking an int and returning an int, I just encode the function signature in the type name. So I call it function int, and this will the base class. So I call it base. And this class will have a function call operator, which returns int. This is a function call operator, and the argument type will be int. I just call it x. And this function I want to be virtual. So I mark the function virtual, and I actually want it to be pure virtual. So I type equals 0. So, and this function int base is now the return type of my add function. But here's the thing. Here there are a couple of problems. First, object-oriented polymorphism in C++ with inheritance does not work on the value itself. I have to return this by a pointer. Okay, and now I have more problems because it changes the syntax, right? I cannot invoke the function through this pointer here. And also the question down here is, how do I tell the compiler that the type of the lambda produced closure object should be inherited from function int base? And how do I return a pointer, right? I cannot take the address here because addresses can only be taken on L values. So this does not work. I need to introduce another level of abstraction. I can hide this polymorphic class here. I can wrap it in my in a custom type. So I create a custom type. Sorry, I create a custom type function int without the base, and internally in the private section, I will store a pointer to the base, call it pointer, and now my function call operator is not public, is not virtual. I remove that and I implement it. I just invoke the function call operator of my polymorphic base type. So that is return ptr in x. But that does not work, of course. This is not how you invoke the function call operator through a pointer. But why do we make it that complicated? Don't use the function call operator, but simply use a function called call. And here invoke the function call. Okay, and now, of course, we don't return the pointer here, but just the function int, like this. And now, you see, the code, the main function should compile now. But what's missing now is that we still need to be able to initialize this function int with our lambda. So what we do is we can also move this base type here, because it's only used inside the private section. We move it actually inside the private section of our other type. And since it's already in the private section, we don't need to have the control of the visibility of the accessibility. We just turn this into a struct for simplicity, and then we can remove this public keyword. Yeah, like, no, this needs to be indented. Okay, like this. So we have our function int, and now we want to be able to construct it from anything. And we need to give it a implementation. So we need to derive from the base type. Just call this base. Right? It's already inside. So we create a templated implementation of this. A templated derived class that we derive from base. And we call it, we also make it a struct, and we call it model, and it inherits from the base. And in here, we want to implement this function, and this is marked override. And we store this t, our template argument, and this will be our closure. And in the function call operator, we invoke the closure, and to return closure, and we invoke it, and we pass x to it, and we return the result. Okay, and what is wrong here? It's semicolon is missing. Good. That still cannot initialize it. We still need to provide a constructor of the function here. We do this, and we also need to make this a template. And we just take t as an argument. This will also be the closure, right? And inside, we just want to set this pointer PTR. So we call PTR, and we assign new model, and this will be is parameterized by the type new model, and we pass the closure. This still does not work because we still need to have a constructor of the base of the model. We also can initialize it with a t. Just call it c here, and we initialize the closure using this. And now the code is compiling and returning the right value. Now we have introduced an abstraction that did not require any changes to neither the client code nor to the code that produces this function int. It still has problems, right? There's a memory leak. We are never deleting the pointer here. We can fix that by using a unique pointer, for example. Unique pointer. And then we have to fix this initialization. Here we write it like this. We just initialize it here. Yeah, and a colon here. And now it should still work. Yeah, it's still producing the right result. So what we have implemented here, this pattern is called type erasure. It's a typical pattern for C++. It's very useful if you want to provide abstraction without falling back to the classical object-oriented approach where clients have to derive from a public base class or from an abstract base class, because that changes the semantics. They now have to pass around everything by pointer. Here, this function can be passed around by value. And I will talk about type erasure in the next video more extensively. But for this particular use case here, where we want to return a callable object, the C++ standard library already provides a solution which is parameterized. So instead of encoding the signature here in the type name, we can pass it as a template argument. It will then look like this. And we also need to put this here. And this will work exactly like our own implementation here. If you look inside the implementation, you may see a couple of differences. First, the function object here is copyable. Since we used a unique pointer internally, our function objects are not copyable. And also, what the std function internally may use are two performance tricks. The first one is it's possible that, depending on the implementation, it does not use virtual functions but function pointers. And the second thing is, depending on the size of the closure, you see here in our closure, we're only capturing an int. So the closure object will just have the size of an int plus a pointer for the virtual function. But so it's the size of two pointers. And since this is small enough, it's possible that the std function stores that inline instead of allocating the object on the heap, like we did here. We call it new. It's possible that depending on the size of the closure, the objects are stored inline, and if it's big, it's allocated on the heap. In our implementation, we just always allocated it on the heap. But apart from those small optimizations, it's essentially the same pattern, right? Where you have a type, you give it a public interface, and internally you use this the abstraction, but keep it as an implementation detail. So with std function, this code works. We can delete the code here above. And as I said, in my next video, I will talk a little bit more about type erasure. So make sure to subscribe, like the video if you like, click like if you actually like it, and then wait for the next video. Hit the bell that you get notifications when I release the next video. Thanks for watching. Goodbye.